So, section 13.7, proof by induction. You've looked at direct proofs before. Most of the proofs you've done in mathematics up to this point have been direct proofs. In geometry, the majority of proofs you did were called direct proofs. You reasoned if A, then B, if B, then C, C, then D, and therefore if A, then D. And you also did some proof by contradiction, what were called indirect proofs in your geometry text. And a proof by contradiction was something along the lines of, hey, either John's in the library or he's in the gymnasium. If I accept that statement as true, and if I go to the gymnasium and he's not there, then I will have proved that he's in the library, because if he's either in one place or the other, and I know he's not in one of the two places, then by default he has to be in the other if I accept that he's in one of the two places. So that was your proof by contradiction kind of backbone, if you will. And so now we're going to do what's called proof by induction. And to illustrate that, we're going to take a look at a sequence of numbers that we've seen now a couple times, you'll continue to see, called the sequence of triangular numbers. And why do we call them triangular numbers? Well, we can form triangles of dots to illustrate these numbers. For example, it's not a very interesting triangle, but the first term 1 is just one dot. And I can form triangles with rows, and in each row I'm going to add now an additional term. So now you can kind of see the triangle emerging when we get to that second term. I form, first row has 1, and then the second row has 2, and now my triangle's underway. I get 3. And then if I add another row here to get to the third term, my total number of dots is 6. If I go to the fourth term, 1, and then 2, and then 3, and then 4 dots. And my triangle continues on and on. So the question is, what's the nth term? So I look at 1, 3, 6, 10, 15, 21, 28, 36, and I go, I don't readily see a pattern. I'm adding 2, and then I'm adding 3, and then I'm adding 4. Let's see. I'm not seeing something real quick like, the sequence 1, 4, 9, 16, 25, and the nth term clearly is n squared. So what can I do here? Well, first thing, I might want to look at this and write this a little differently. From looking at the actual triangles, I saw that I've added each time the number of dots that's in the place where I am in the fourth position here, the nth position. I've added 4 or n dots. So if I were to rewrite this thing a little differently, I can look at, to get to this, say, second term, what did I do? I did a 1 plus 2. How did I get to the third term? I then looked at a 1 plus 2 plus 3. How did I get to the fourth term? I had a 1 plus 2 plus 3 plus 4. Therefore, I can view this fourth term really as the sum of 1 plus 2 plus 3 plus 4. That's my 10. This was my 6. This was my 3. Obviously, the first term is 1. So I look at that. What are these terms then? What is each of these terms? Well, it's the sum of the first n terms to get there. And I look at that and say, well, okay, I can recognize that. That's a arithmetic sequence. And the sum of an arithmetic sequence is, the sum of arithmetic series. If I add the sums of the terms of the sequence, I get, my sum is going to be n times t1 plus tn all over 2. So therefore, in this case, if I'm trying to get out here to, say, the term out here, the 28, 1, 2, 3, 4, 5, 6, that's the seventh term, that would be n times, well, let's work it out. Let's see, we've got, if I look at this, my first term is 1. I do have n terms. My first term is 1. My last term is n. And I do have n terms all over 2. So to get to that seventh term out here, the 28, 7 plus 1 is 8. 8 times 7 is 56. 56 over 2 is indeed 28. How about the ninth term? 9 times 9 and 1 is 10. 10 times 9 is 90. Sorry, 1, 2, 3, 4, 5, 6, 7, eighth term. Sorry, eighth term. 8 times 9 is 72. 72 over 2 is 36. So one way I could have come up to determine a formula, explicit formula for the nth term of this sequence is to recognize that each term is the sum of the arithmetic series beginning with 1 and going out to n. So indeed my formula here is Tn equals n times n plus 1 over 2 for this set of triangular numbers. Let's look at it a different way. Suppose someone tells me, or I somehow stumble across and see that the nth term of this sequence is n times n plus 1 over 2. And the pattern looks good. I mean, if I let n be 1, 1 times 2 is 2 over 2 is 1. That looks good. If I go here to the second term, 2 times 3 is 6. 6 over 2 is 3. That looks good. And we go through and say, well, yeah, the formula looks good. It works for all these terms. The question is, how do I know it works for all terms? And this is where proof by induction is indeed a very powerful thing. And to give you an idea of how proof by induction works, it kind of, you want to think about our recursive definition a little. It's kind of related to recursion in the following manner. Suppose I want to prove that this formula here works for all terms. Here's my strategy for proof by induction. Show that it's true for the first term. So show true for n equals 1. And then that's step 1, and that's always pretty easy. The next thing I want to do is assume true for some term out there, for some kth term. Now I know we're using an n up here in our rules, and you're saying, hey, now why are you introducing this k? Well, because I want to prove the formula is true for the first n terms, but before that nth term, there's some other term, the kth term, and I'm going to assume that the formula is going to be true for some n equals k, and if when I do that, assume true for n equals k, and this is key, and then show true for n equals k plus 1. And you may say that's a pretty innocuous looking statement, but it's very powerful, and here's an analogy for how it works. What have I done? Well, let's imagine metaphorically that I want to climb a ladder over here. Here's my ladder, and the ladder, though, is a special ladder. It has infinitely many rungs. How could I be able to climb that ladder as far as I wanted to go? I'd have to be able to do two things. If I want to touch every rung on the ladder, I would have to be able to get to and get on the ladder at the first rung. And that's the equivalent of showing my formula is true for n equals 1. You need to be able to get on the ladder. And I'm trying to prove that this formula is true for all n terms, so I got to show that it's true for 1. Now, next part for the ladder. If you get in the first rung and you want to be able to climb every rung on the ladder, you got to be able to get from a rung somewhere to the next rung. So this would be, say, my kth rung here on the ladder. If I can get from k, the kth rung, to the k plus first rung, in combination with being able to get on the first rung, I will be able to put my feet on every rung of the ladder, because if I can get to the first rung using the second rule, I can get to the second rung. And if I can get to the second rung using the second rule, I can get to the third rung. And that simply continues on and on and on. So those are my two steps for proving something is true by induction. Show formula is true by induction. Show it's true for the first term. Assume it's true for n equals k, and show true for n equals k plus 1. So how the heck do I do that, though? I do exactly what those two steps said. I write down show true for n equals 1. And it seems silly to do this arithmetic, but this is what you want to show in your work. For n equals 1, does 1 equal, and I put a question mark because I'm trying to show it, does 1 equal 1 times 1 plus 1 over 2? That's plugging in n equals 1 directly. Simplify that, equals 2 over 2 equals check 1. So that's half my proof for proof by induction. I've shown the formula is true for n equals 1. Second part's a little more complex. Assume true for n equals k. If I do that, then 1 plus 2 plus 6 plus 10 plus dot 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 plus k. I'm supposed to show that that equals k times k plus 1 over 2. So I'm going to assume that that's true. Show true for n equals k plus 1. So I need to show 1 plus 2 plus 6 plus 10 plus dot 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 plus k plus 1 equals, let's see, if I look at k plus 1 for my formula, I'd have to show that that equals k plus 1 times k plus 2 all over 2. The question is, how am I going to do that? And the key is I want to look at the left side here and compare it to the left side here. What's the difference between these two left sides? I've just added a k plus 1. So if I'm assuming this is true, and I add a k plus 1 to the left side, to keep things equal, I have to add a k plus 1 to the right side. So this question boils down to saying, if this is true, and I add a k plus 1 term over here, I'd have to add a k plus 1 term over here. And then if I simplify this expression, k times k plus 1 over 2, if I simplify that, does it turn into this? So let's continue here. If I add that k plus 1 to both sides, I'd have 1 plus 2 plus 6 plus dot 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 plus k. Add that k plus first term, then that's got to be equal to k plus 1 all over 2 plus k plus 1. And now I've got the left side here with that k plus first term added. The left side here with the k plus first term added equal to the left side here with the k plus first term added, because I'm going out the k plus first term. All I need to do is show that this expression right here equals that, and I'm done. So can I do that? Well, let's find out. And here's where my algebra skills come into place. Find the common denominator. I get k times k plus 1 over 2 plus common denominator of 2. That's going to be 2 times k plus 1 all over 2. Find that common denominator and simplify. I get a k squared plus 3k plus, let's see, 2 all over 2. And then I can factor that expression, and I get a k plus 2 times k plus 1 all over 2. And I then can factor that out, or so not factor it out, but I can rewrite it as k plus 1 times quantity k plus 1 all over 2. And I want to look at that for a minute. I now have shown that this side right here simplifies to this. What do I have in the left side? I have the sum out to the k plus first term. I needed to show what? I needed to show that that sum was k plus 1 times k plus 2 over 2, or k plus 1 times k plus 1 plus 1 over 2. And indeed, that's exactly what I've done. I want to show true for k plus 1. Well, the formula is supposed to be then k plus 1, and the next term would be k plus 1 all over 2. Voila.